Excuse me. Alright, Lulu. Let's see, it was some time since I was on here. Yeah, still thinking about this issue here. This is a real blocker right here. And I haven't really gotten any new ideas for this. Sometimes it helps to like go back, spend, you know, have it in the back of your mind a couple of days, come back to it, and then it's like, oh well, let's try this idea. But no, that unfortunately has not happened. And I think I'm gonna try do this, I guess, next best idea of storing kind of like a closure on the heap that we can access here. Now we just need to make sure that whatever we store, wherever we're pointing to from that, is available as well. So basically nothing from another thread's stack or anything like that. Like either a thing is stored on read-only data, which is, you know, parts of this is stored on read-only data, and that is fine to point to. That is always available. However, things that are on the stack is not guaranteed to be available, especially cross threads. This is stored technically now on the heap, which is also safe to use unless we start to introduce like garbage collection, although then we need to make sure that whatever we're using should be available, like some kind of reference counting, for example. Yeah, so the thing we need to make sure is when we set whatever items we set on the closure needs to be available, of course, then but that should be fine, I think, for now. I don't think we're gonna go with another register. Where I think what we're doing is we will simply add another thing to this stack operation. So basically when we fork, we push a bunch of things on the stack, and the fourth element is always going to be the pointer to the closure. Now I'm thinking maybe, yeah, and then it's going to be like comp time known if we're like pointing to, like if we're using X here, for example. That means that, okay, we're pointing to the closure somewhere on the closure, and that is comp time known, so that's fine. The thing so that should all be good, but the thing that is kind of bothering me right now is that, okay, well, now we're deep in some kind of a nested thread thing here. How do we now bring this out here? So basically, how do we now take X and bring it in here? That is the question, because we need to kind of transition between not only one thread from the outer thread, but into this block here, which is another thread, and then into here. So that is now the issue here. Hello, Piano Coder, thank you. Welcome back. How's it going? So yeah, so that is the issue. And I was thinking of some kind of context thing where each, like we could have a thread stack maybe. Perfect. Wow. That sounds really nice. Almost too good to be true. What about you? Yeah, I'm good. I've been busy with work, unfortunately. I mean, I would really like to work with this, with my own stuff. But yeah, I won't complain though. I have a job, and that is very good. I have a very nice job, so I won't complain too much about that. But I want to move to, of course, just doing my own things. But we'll see what happens. Maybe it happens, maybe it doesn't. We'll see. Yeah. So maybe we could allow... No. Or is there another way to do it? Like, could we just copy... Yeah, one thing that I was thinking about is labeling these. Creating like labels. But that was for the stack though. Yeah, one day maybe. But you were working, or did you study right now? Let's see. And what would that mean if we had a context stack? We create a closure for this thread. We could probably reuse that for functions as well. So we create a closure here, and we have a thread stack, and we require X. If it's not available in the scope, we create a closure and try to look at the outside. If it's not available here, we have to do the same thing again. We have to create a closure. I think. And then look at the outside, and there is X, so we can wire that up, but that means we need to like insert instructions like at an earlier point as well. But that could be so okay. So maybe we need like 2 compiler passes in that sense, or we just insert a bunch of instructions at certain points. Because it's like when we're down here, we already compiled a bunch of stuff up here. And it's like when we encounter this reference, we're like, oh shit, now we need to wire up a closure, we need to add X to it. Maybe all threads, maybe we'll have a closure for all threads by default. But then, no, that's stupid. And also at the end, no, okay. Well, we don't really have a free instruction, so we don't really care about like memory management right now. We're just allocating this closure. Okay. Man, this is the hardest problem I think that I've had this in this project. Okay, but this is not. This is gonna be like S3 plus 0. So that is. This is gonna be X here. Yeah, in this scope. And then we have to do it again. So it's gonna be brought into this scope and then brought into this scope. Although, do we actually have to do that though? That's the question. Like, we probably don't even need to do that. Like, but the thing is, no, we don't, because we need to create this closure. But okay, actually, you know what? Another question then is like, okay, well, let's say we have another thing called Y here, which is also from block thread. I'm just gonna do this too. So now it's on the heap. Okay, so now we have two different things, and then we're also gonna say, you know, Y here as well. Okay, so now we're referencing both X and Y from this inner thread, which means that, well, X is grabbed from out here, and then Y is grabbed from here. So we actually need X to be brought in from this place. So whenever X is like defined, basically we have to add it to the closure. The problem is, how do we keep track of the closure pointer to do that? How would this even work? Like, we could create the closure here, but then we fork directly, which is not we fork directly, which means, well, when here we're gonna fork into here first. And then once we're in here, so this closure is for the block thing. And then we're gonna have another closure that is gonna be for the execution here. And then you're gonna be Y T0. What the hell? Now let's remove this. I don't know why I put that there. So allocate one. That basically, this is setting R to be, you know, some kind of heap there, pointer. And then we're setting R to be, we're setting the location here to be X. So we're storing X on the heap basically. And then we're forking with R as the closure pointer. But then set 4 is basically, it's basically, you know, this is not really an instruction, it's basically just saying that X is stored at this location. And then we have Y as well, and then over here we're gonna have a closure for this one. The problem is, where does it find X? I guess the problem is like, how is this compiled? This whole thing here. So it's gonna be an argument into echo, yeah. So it's gonna be in the thread of the execution. Y is just gonna be at the end. So this thing is gonna be put on the heap. Actually, it's gonna be like a string or a slice of like 3, or well, technically it's like 1, 2, 3, but whatever. It's 3 elements. So you've got this interpolation, this string, and this interpolation. So this thing is then from the closure. Right, that can be declared through the scope, so that's fine. And then this one is also going to be in the scope, I guess. It's going to be like, but it's going to be in the outer scope. It's actually not in the scope. Actually, none of these are in the scope from the start. But once we create the closure, this is going to be on the in the scope, and it's going to point to the closure here. But this one also needs to be there. However, the thing that I'm thinking of, it could be referring to the parent thread's closure, although that's also bad because that could be like deallocated, although we don't really have the allocation right now though, so it's probably safe. But in the end, we do want to have like the parent thread is gonna, like, if it quits, the closure is probably gonna be cleaned up, and then this X has to refer to this thread's closure, which is over here. So we probably need to allocate 2 things, and we're setting, you know, this is, you know, we could do this. Well, the notation is more like this. So we do the first element of R is set to Y, second is set to X, or the other way around. It doesn't matter. I guess it would be the other way around. I don't know. It depends. I guess it depends on in which order this is compiled here, down here. But basically, we're filling up this closure. We're allocating that, doing that, and then in here, Y refers to R, or not R, but the closure, or S, yeah, stack 3. So this would be, so set 5. We have X equals to set 3 plus 0, and Y equals to set 3 plus 1. Okay. And the thing that we're missing to do this is modifying the instructions like after the fact to add these. Like, even if we added the basic, like, generic closure things like alloc, we still want every time we encounter an identifier that is not in the current scope, we need to add it to the closure. So that will modify the instruction set after the fact. Like, when we're in here, we're gonna have to modify like instructions before, which should be fine, hopefully. And then yeah, and then we have to push these variables on this inner scope, and they have to point to the correct place, whereas, you know, S3 plus 0, S3 plus 1, so closure variable number 0, closure or value, closure value number 1. So that's fine. Yeah, so we need like that stack. I think the scope stack could be 1-to-1 with the threads then, probably. Maybe. Maybe it shouldn't be. I mean, because we're gonna have scopes like, we're gonna have like this is an inner scope. Although the block is always in a different thread, so maybe we actually do have different threads. What if we have like if else? Yeah, those also, like all the block expressions are technically its own thread. So actually, I think that scope and thread is actually 1-to-1 in this case. All right, we'll get started on this. I'll just need to BRB 1 second here. All right. Okay, let's just try this here. So, oops, let's see. No, we'll go to the compiler. Okay, let's just assume that the scopes are going to be, so each frame is going to be like its own thread basically. So it's like when we do a lookup and we don't find the binding in the current scope. So first of all, I think that we should only have like one type of frame here, which are the bindings. Yeah, that makes sense, I think, because yeah, I think I made it like this because the older thing was the previous implementation. I had like a whole bunch of different types of scope that all shared basically the same stack. But now we kind of want to, I mean, I guess we could still have that. It's just when we do a lookup, we have to find like, we only look at the first frame that we find. Although we still want to do a lookup to try and find like we want to have like a shallow lookup and a deep lookup, I guess. I'm just gonna add options here. Shallow, let's set it to false or something. And then it's like, okay, well, if it's shallow, we want to have like a bool found frame and well, actually let's do it like here instead. So let's say either we find it or else if it's shallow, we return null to say that we didn't find it in this scope. Otherwise, we want to continue. So if we are doing a deep search, we continue through all the frames, through the whole stack. And if we do a shallow one, we don't find it in the first frame, we just return null. All right, and then we probably need even more things later, because we want to see, okay, well, we didn't find it here, we probably want to find it later, like later on. We want to find it in a different scope, because we could be deep in the stack somewhere and referring to something way outside, which means that each step through the stack needs to add it to its closure. And I think we also need to kind of extend the frame to not only have bindings but also have the closure definition as well. So I think we'll change this to a struct. And I'm gonna rename you to push. Okay. And so we're gonna have the closure. The closure, what is that gonna be? So we basically just need to store like a list of identifiers that's going to be stored in the closure, and they are going to be ordered in a certain order. I'm just thinking of how like this one, for example. X and Y. Yeah, I mean, I guess it's the same for each one. Like X, it's just an identifier and which order it is. So X is stored at the first position, Y is the second position, and then over here we get X and Y like this. What other things do we need to do though? I don't think we really need to do anything else for the definition of the closure. No, we just need the identifier name and the order, which is, you know, part of the array. So this would just be an array list of names, I guess, of identifiers. Can we do this maybe? Okay. This one doesn't really make sense now. Actually, let's no, it's basically yeah, maybe we want to keep this logic here, start frame or start depth. Okay, maybe we'll do this. We'll rename this to get frame. We'll delete the tag because that doesn't make sense anymore. And start depth. I mean, this is basically getting the frame at this depth, basically. And it doesn't make sense to get a depth back now either. So we'll just get this. If the depth is more than this, that's fine. And then we basically just, I mean, we don't really need to loop here. We can just say depth and we'll return frame. I guess it also has to be more than no, that should be fine, right? Hello, Speed Speed HQFX. What's up? Welcome. What result are you wanting to achieve? I will provide you with the answers that you seek. What? I'm trying to figure it out by myself. Thank you, though. What kind of answers can you give? Like what? What could you help me with? Alright, so we'll just get that frame. So this just gets the frame at the end. Or the current frame, I guess. And since we don't return a tuple, we can remove this. And yeah, I guess if length is 0 and depth is 0, this still like this. Yeah, then we don't. Yeah, so this should not be an issue here. Yeah. Tell me the results you wish to achieve. Are you gonna prompt AI or what are you gonna do? Oh, you're a master dev. Okay, cool. Well, as I said, I try to figure things out by myself. If people want to help me discuss things and reach some kind of answer to some discussion, that's fine. But I would rather try to figure things out by myself. But I mean, have you ever implemented a compiled language before? I mean, saying you're a master dev is fine, but it's also like a dev can mean a lot of different things. Because you can be, you can be a web dev, you can be, specialized in different things, which would grant you a lot of knowledge in that specific area, but then maybe lacking in others, because there's so much in programming that many developers don't even touch in their whole lifetime. Let's see. So, right, frame bindings, but yeah, that should be the same. Oh, hang on. All right, and then we got lookup as well, and of course, this doesn't work now, so we remove that. And yeah, new depth is gonna be like, depth plus 1. So I'm just gonna do this instead. Okay. This looks so much like Go syntax and stuff. I guess. I mean, I think it looks a lot like C as well. They both have a lot of things in common. Although Zig does have a bunch of stuff that looks different from Go. Now, I'm not a Go developer, but I've seen a little bit. I've tested a little bit, but yeah. I think this thing is I've not seen in other languages. I'm not sure if this exists in other languages, like this syntax here. Like capturing, it's called a capture. which is interesting. I really like the zig syntax. I am building a NL input to NL compiler that spits out domain-specific DSL. What is an N? That is hard to say. What is an NL input? And what is an NL compiler? Well, that sounds like a really interesting project. Is it like, how does the DSL then work? Like, is it compiling to native code, or is it like interpreted or transpiling to something else, or what is happening? Natural language. Yeah, that makes sense. User input natural language prompt. Okay, so it's a AI based. Interesting. How's that project going? I mean, it sounds very impressive. If you could get it working, that would be really cool. Alright, so lookup gives you the thing, otherwise it doesn't give you the thing. Maybe we need which frame it is, or which depth. I'm not sure. I think we need like a recursive operation. Like, if we try to find a thing, we will create a closure, add the thing to the closure. Actually, first we need to do a deep lookup to see if it exists at all. If it doesn't exist, then that's an executable call. If it exists, we need to kind of do a recursive operation where we create a closure, declare the variable, or add, yeah, we add it to, we have a closure already, but we add it to the list of things in the closure, right? And then we also need to declare the thing, the variable. Well, that should be easy actually. And then we do it recursively until we find which frame actually has the source of the thing. Yeah? Okay. Work in progress. So, okay. Well, I'm curious. How many years of experience do you have, like, developing? What do you want your script to do? What script? So I'm building a language that is that is going to be able to interpret, or I'm building a program that is able to interpret my language called Runic. And yeah, it's basically gonna be like bash. So I can show you here because I have this prepared basically here. So basically, on the left hand side you have Runic, and on the right hand side here is bash. And so basically it's gonna be like a kind of replacement for bash for my own personal use basically. Although it is going to be available and all that, you know, for anyone to use if they want, but it's mostly for it's for my own purpose, and it's also you know, for what do you call it, like yeah, just it's fun to actually create the language. So you can see, like, it does look like Bash a lot. You know, you can call programs like this same way as in Bash. And then we have, like, you know, here you can see the differences between, like, things like if statements and these things. Hold on, are you building your own computer language? Yeah, building a scripting a scripting language. Yo, Penguin, what's up? Welcome back. So, yeah, you know, if you're familiar with Bash scripts, it's basically going to be the same thing, although it's not going to have all the bells and whistles that Bash has. But it's going to basically, I'm going to try to cover what I'm kind of using from Bash to be able to create my scripts without having to use Bash. Basically, because it's like the reason is two things basically. Is one, it's fun to make a language, and two, I'm just tired of having to look up the syntax of Bash all the time. And even if I were to use something like AI, because I've tried this, it's you know, when doing Bash scripts, it does work fine most of the time, but sometimes it does these weird things, and you get these weird bugs, and it's hard to kind of understand what's happening and try to fix those. So I would rather just be able to more easily kind of write my own scripts. So are you building a compiler? Well, not compiler in the traditional sense, I would say. Like, I have, like, what you could say is like, well, it's kind of like a compiler. I have, like, the parsing of the source code into tokens, and then into parsing those into an AST, and then that AST is then compiled, quote unquote, into an intermediate language. So it's actually two languages, you can say. So it's one language is this one, that is the one you would write in the scripts, and then the other language is more like a type, like an assembly type language, which is called like an IR, which is kind of what you're seeing here in my comments. I'm trying to kind of figure out what I need to turn this into. So basically this is translated first into a bunch of instructions like this, and then those instructions get executed through an interpreter, basically. So, and that's how the program is run then. So it's not compiling down to native code like an executable. It's not compiling down to an executable program, but it is compiling to kind of like an assembly-like language, and then that language is like interpreted and executed as a script, sort of. Is it spec driven? I'm not sure if I understand what you mean. Why is YouTube deleting my comment? I have no idea. Are you trying to post links? Because I think the Nightbot thing is like getting angry when you do that. Okay. Right. So I think, well, for one, I need to go here. So here's the thing. Whenever you add a set, an instruction set, that is meant to be ran in a separate thread, virtual thread, runic thread, I should say, just to don't mix things up here. Then it probably isn't. Well, what do you? Okay, could you explain what you mean by spec driven? Post a GitHub link for you to guide me on how to improve. Oh, sure, I can do that if you want. Maybe I should get rid of Nightbot. Nightbot has only been causing issues. Like, people can't post links. Like, I understand that it can be people would post things you don't want, but you should be able to post links. Or maybe I could just fix it. Hang on. Where do I have this thing? Timeouts. Hang on. Moderation. Links. Alright, so I disabled link filter. Wait, but this is the wrong. Hang on. Okay. I think now you should be able to post a link. Sorry about that. Official. Alright, I'll take a look. So what repo would you like me to look at? Been unemployed since 2023, since I passed out of college. Would appreciate if you could guide me to land my first job. How many jobs do you apply to? Because it's basically just trying to, as people say, it's like a numbers game. You just have to apply and apply and apply until you get one. A system that, so you're answering my question what spec-driven means. A system that follows a set of deterministic specs that makes it replayable. Robotic software is spec-driven due to AI having to be constrained. I mean, the compiler is deterministic. It's not going to be indeterministic, because you're gonna get the same program every time you compile. Or I'm not sure if I understand. A dozen applications in a week. Okay. Well, are you building, like, in the meantime, are you building, a portfolio that you can show? Because obviously you need to, obviously the more you can show, the more skill you gain while developing, and the more you can show to so that they can see where your level is, basically. But I believe right now it's pretty hard for juniors, unfortunately, which is unfortunate. I think that's what I've heard, at least. Yeah, I'm not sure if I understand what you mean by spec-driven in this context. Do you think software development is moving towards prompt development? I mean, I'm using prompt. I'm using AI right now to kind of help me. I mean, at my day job, we're using everyone is basically using AI to kind of help with development by like speeding it up. But it's not replaced entirely. At least not right now. There's a lot of issues still with AI. And you can't use it as like this magical tool, which many people believe that you can't use this as a magical tool that will solve all the problems, because that's not how it works. But it can be used to improve productivity of a very. That it can do, but you have to kind of learn what it's good at, because it's good at certain things and bad at other things. And what I'm talking about now is like, well, me personally, I'm using Codex a lot, but then there's others using like Claude, Cursor with Claude and other things. And I mean, that's basically it, like just some kind of agent type AI that you can instruct. As long as you can instruct the AI to do the things that you want it to do, then it's good. But it's like it's not good at certain tasks. It's very good at certain tasks, but then there are other tasks that it's not that great at. So you kind of have to learn, like, okay, what can we use it for? And also, once you've done something, you always have to, we always have to test, obviously, a lot to see that it actually works, what it's doing. And then, but then also, if it's like, if you're doing something that requires some kind of security, of course, you have to kind of double, triple check the code. Or just write it yourself. Like some things, it's way faster to write yourself instead of having AI try to do it. And it's what I've discovered is not really that great at like UI development, especially if it can't actually see what it's doing, like the result of the code. And then you try to kind of instruct it, hey, this thing over here is like, can you change it to this? And then it doesn't really understand what to do. But I'm gonna try more to see if it helps to show it, like being able to kind of emulate the web page that it can see what's happening. And maybe that will help. CLI are better. I mean, I think they are the CLI is like, I'm using Codex, for example, that has access to so many things. Like I'm using MCPs to, be able to access all kinds of stuff. So instead of it hallucinating a bunch of things, you can have an MCP that will, tap into some kind of design program that will, see what designs we need to have, or it can tap into, the task management platform to see, okay, does this implementation align with the current task, stuff like that. So it's like, it's really nice what you can do with. So it's like, yeah, you could just ask it a question, and it could go in and tap into all these things and give you an answer, basically. But yeah, I would use it for like boilerplate tasks. If I want to find out maybe like a bug that seems to be tedious to solve, I would say, that is good to use AI to kind of just launch it. Okay, try to figure out this bug, and then you will actually work on something else in the meantime, and then AI gets back to you and maybe solves the problem. Hey, hello, Subadarano, welcome. Just came back from school. What are you creating right now? Can you tell me how I start making my own programming or scripting language? Well, thank you. Yeah, so right now I'm creating a scripting language. I can show you here that if you're familiar with Bash scripts, it's kind of like, you know, echo hello world. This will so this on the right hand side is Bash. So this is like the, you know, standard Bash language that I guess a lot of Linux users are used to. And then on the left hand side is my new language here that is gonna kind of do the same thing except slightly different. And so yeah, so here's basically, you know, you're executing the echo program with hello world as an argument, and over here is like, you know, the same thing here. And so the difference between the languages is basically the syntax of the kind of the programming parts. So here you have like an if statement in Bash, and here's my version here, which is basically taken from how Zig works, but it's also with, you know, a little bit of a twist because it's like a different language. And yeah, I have the opportunity to kind of change things a little bit to my liking as well. But basically, creating a compiler consists of different components that kind of work together to make what you want to make, and there's like separate steps that you need to do, but it's like the normal kind of the standard thing to have is first you have a thing called, well, first you have the source code, right? And then you're passing it through something called a lexer, which gives you a bunch of tokens. And a token is basically, you know, you're taking, because the source code, like in the computer, is just a bunch of bytes. It's just you know, it's a bunch of characters with no real structure to it, other than the order in which they come in here. And then the tokens are actually more structured. So the tokens, so this thing here, basically, you can turn into a comment token, for example. This thing here could be turned into an identifier token. So echo would be an identifier. Over here, this would be a string token, and so on. So you would get, so all these bytes here, or characters, are turned into three separate tokens. So that's the tokens. So it's basically just, it's not like you have to do this step, but it helps a lot when trying to build a parser later. So you take these tokens and you pass it through something called a parser, and you would build this yourself. You know, you can build it yourself. There's probably, you know, libraries that will help you do this and that, but this is the basic building blocks of a compiler. So you pass the tokens through to the parser, and the parser produces something called an AST. It doesn't have to be in a tree form. Like this is an AST, although the name is abstract syntax tree. And it's basically just a fancy way of saying it's like all the compilation nodes. So basically this expression over here is gonna be like, you know, call executable expression or something like that, with echo being the executable name, and this is like the first argument. So it now you're structuring even more. So you're turning this into a full-on structure. And I would say the parser is probably it's by far the most complex thing in this list here. And then now you have kind of like a choice. It depends on if you want to make, because the AST itself, it's like it's used for several things. So you could now compile it to something else. Like you can compile the AST into another language, which would be called like transpiling in some areas. You can make it into native machine code, which would be like the classic compiler. You can also interpret it directly if you want. If you can do that as well. So here's like a choice. It's like, but these are usually the things that you would start with, I think. And then you would like, let's say you want to compile to native code. Then it's also, here you also have a choice, because you can either try to do it like yourself, compile down to native code. But I think most people would probably use something like LLVM IR, which is like you're compiling down to another language basically. So you're turning this into a language that is part of the LLVM suite, which then has, once you've turned it into this language, you can then use like LLVM compiler to turn this into an executable. So there's, if you want to make this all the way here, there's a lot of things that's happening with a language if you want to make your own compiler. But I would suggest starting over here and then maybe make some kind of interpreter to interpret the AST. And then think about continuing here. Because this is a lot of things, just this part here to start with. Especially if you're like new. So yeah, by the way, good news, I just got Zig set up on my PC and not gonna lie, so live circus C just use so many headers, while Zig is like, okay, when I import, what's the file name? Yeah. Well, yeah, I mean, I would say like Zig is good, is a good replacement for C, is a very good replacement for C. But one thing that you have to look out for is like the documentation is lacking in certain areas. It's not like a fully released language yet. And so I haven't really gotten into any kind of compiler bugs or anything like that. But so the programs feel very stable. So I mean, I've not gone into some weird issues like that, unless it's like my own fault, like with messing with pointers and stuff. But the thing I would say also is like Zig doesn't really have a lot of Stack Overflow questions that you could search for. So if you wanna have a language that you can kind of, I reached this issue, how do I solve it? You kind of have to work it out yourself. It's like there's not a lot of help to get. Although I would say there is a very good Discord channel for Zig that has a help section that you can ask any question you have on Zig, and people will come and try to help you there. And that is very nice. So that is kind of like its internal kind of Stack Overflow, I guess, type thing. And you can also search there to try to find answers there. But yeah, I would never go to C now. Like if I want to have a low-level programming language that is like C, I wouldn't go to C. Although I might do it just to try it, because I've never actually done like a larger project in C. But I can already, you know, by the features that it has, if you compare it to Zig, I would prefer Zig. Just because of the things that you said, like whenever you include something in C or C++ even, you know, you're polluting your scope with a bunch of invisible things. And in Zig, that's not the case. Like everything is named, like everything is explicitly named, and you don't have to worry about that. So the whole system works a lot better, I would say, for that. And of course, the macro is replaced by like comp time things, and yeah, and you can basically do everything you can do in C. You can basically do in Zig. I would probably be brave enough to say. But yeah, this is the basic like compiler kind of pipeline here. And I mean, I'm not an expert, so there might be other things as well. But as I see it, this is, you know, the basic building blocks of the compiler here. But then there's a lot of things you have to figure out. It depends on what kind of language you want to make, how complex it's gonna be, you know. Yeah. All right. Let's see what we are doing here. Okay. Right. So what we're doing right now is we are working out closures, basically. So what you see here is a block. So these things, curly brackets, are surrounding a block of code. And this block is basically, it's ran in its own runic thread, virtual thread. And what we're trying to figure out is if you refer to a variable from inside this thread, how do we wire it up from outside? So this X is defined over here, and then there's no problem in like referencing it in other places. But if we're in another thread, that becomes a little bit cumbersome. So what we need to do is basically define closures. And the closures, how they work right now, is basically we push up, we create a closure on the stack, and we put a bunch of pointers there, and then we when we create a new thread, we push the pointer to the closure when we create the thread. So that will give us the ability to actually refer to these things from the closure. So X is now defined as the closure pointer plus 0, so that's the first element here. So basically we're copying pointers, and then we're redeclaring these variables to mean different things. So X now means stack 3 plus 0, and this means stack 3 plus 1. Yeah, so that's what we're doing. So basically here is like, okay, we're doing a lookup, and let's see, you need options. I think actually we want to add the options here as well. So this would be like scope lookup options. All right. Right. So when we compile an identifier, we are always like in a scope, and each thread, each like runic thread, it's its own scope. And so it's like, if let's say we try to find an identifier, we need to change this code here, but when we try to find an identifier, it's like, okay, well, let's try to find it only in our current scope. If we don't find it, that means we're now referencing something outside of the scope, which means we have to have a closure for that. Okay, so that means that, hey, now we need to add it to our closure. Well, actually, okay, before we do that, let's do a deep lookup to see if the binding, because the thing is, if you're referring to y here in this expression, for example, then of course you're referring to this y here. But let's say you want to have another thing, and let's say you have like echo hello. Okay, this is also an identifier, right? But it doesn't exist in the scope, and whenever something doesn't exist in the scope, or I mean at all in any scope, then we interpret it as an executable that we're trying to call. So this would be the executable there. So if we then go over here, you can see that, well, if we didn't find it, we kind of interpret it as an executable, and we return that. So that should still be the thing we need to do. But now we need to also create a closure if the binding wasn't found in the current scope. So I guess we'll do like if lookup identifier name, and then the options, we say shallow equals true. You have to add the options here as well. Shallow equals false. If we find it in the current scope, we get the local binding, and we return that. Okay. Otherwise, if we're down here, that means that the binding does exist somewhere, so it's like a variable of some kind, but it doesn't exist in our current scope. So we need to wire it up. We need to actually create a closure. We need to add it to our closure list. So let's get our frame here. No, that's a different frame. We need to go to like scopes, and we need to get the current frame. Actually, let's do Okay, I think we're missing a few things here, because we're never really implemented the scopes fully here. So these functions over here, we have push and pop. We're not really using those. We also have get frame, of course, declare, lookup. So what we need to do is we need to add a thing to the closure. So we're gonna declare closure value, or declare closure thing, and it's gonna be like identifier name. Wait, do we need a name? Yeah, I think that's what we need. Actually, let's just put the identifier down, because that's what we, I think, stored there. And that's it, I think. And then what we get back should be the location of that value in the current scope. So this would be the closure value location, which we then return as a result. And I think that when we do the declare, we should declare it in the scope as well. We declare it in the closure and the scope. Yeah. All right. So now we just need to, we need this function here. Let's add it. Let's just add it over here. And we need the identifier. And you will be a location. Okay. So now we want to say we want to get the frame, which is going to be scopes get frame 0. And if we can't find that, we will get some kind of error. Scope not found, maybe. Okay. So now frame should be okay. Let's do a try. There we go. Now we have the frame, and actually, you know what? This should. I think this doesn't actually. Yeah, this doesn't return an optional anymore, because before it was kind of working in a different way. So this is actually not an optional. So let's just do that. And it's not an or else anymore. All right, so there we go. So now we don't have or else. We only get like an error if we can't find it. Okay. So we got the frame. So what we need to do is we need to declare closure value identifier, declare closure identifier. And then we also need to declare a scope binding as well. I guess binding is a good name. But then, so this is basically, we push this identifier here. Now, I guess it would be kind of an error if we already have the identifier in here. That would be like a compiler bug. So I'm just going to assume that that's not the case. So, wait. Where's the allocator? There's the allocator. Okay. And we just pass the identifier in. Now this identifier has like a name and a span, so that's fine. Okay, so that's the closure, and now we need the thing here, binding. So we could say, yeah, we do have like the declare thing, declare function, which actually does declare something like an actual thing into the scope. But now we already have the frame, and then you would declare it get frame. I guess we can add the declare here as a function actually. So let's go here and we go to U and add a declare function, and it will be self is and then this would be like plain declare. Alright, because now we can say declare here instead. Names, identifier name, result. Oh yeah, so result now. So result needs to be the location of the thing in here. So the location is kind of known here because it's going to be the stack pointer or the stack. Well, it's going to be stack 3 plus whatever length the closure is at before we modify it. So this would be the relative index, or the index of this value is going to be the closure item's length. Okay. Of course, try here. And then the location of this thing on that's going to be put on the stack. No, that's going to be put into the scope is going to be from, so this is a result. And it's going to be from location. And we have like init init add, and this is going to be stack, right? Stack 3, that refers to the kind of hard-coded address of each like thread's closure pointer. So it's going to be 3 plus and then index, right? And then we have options as well. The options have dereference. Is it going to have dereference or not? Not sure. It's kind of like a pointer to the local stack plus index. I guess this is fine. And then when, okay, we can figure it out if it needs to be dereferenced later. Not sure if it should be. I think it should be a pointer to that stack location. Yeah. Okay, and then when we declare this variable, so in this thread scope right now, if we refer to this variable, it's going to point to this location here. Actually, let's make this location instead. And then here is going to be .from. And mutable is interesting. An interesting. Okay, this is actually interesting because we're kind of copying. So at this point, I think if we make it mutable, what's going to be mutable depends on what the value is. Like if the value is like a number, it's actually going to be copied and not actually, I think anyway. It's kind of complex right now. It might be copied and not mutable or mutated if you mutate it from within the block. But if it's something stored on the heap, for example, it's going to be actually mutating the original heap located thing. Well, I guess make it mutable makes sense to have as a thing, but then it might not work right then. There might be bugs with that, but yeah. Okay, so and then at the end we would return. What did we actually want to have? I guess it's the location of the binding. Yeah, so it's going to be the same location here. So there we go. All right. Expected result found. Oh, I need to try that. Binding is not used. Okay, I think we'll just toss this here. Unsupported. Oh. Right. Hang on. Where's that dot from? Oh, so the location. Wait. So this one returns an error. No? Because this should be a location. What is it complaining about? Result from. Maybe I had it somewhere else. Maybe it was this one? Oh yeah. So try here. And you could get the full stack. I just have I'm actually like in my setup with Zig here. I actually haven't set up so that I see the where the error is happening for a certain thing. Like if you have a compiler error happening, like a compiler error, like this compiler error. Wait, do I have to do this? Wait, no, compile error. Here. So if you have this happening, it's kind of like you get the error here. You don't get the error where kind of the source of the issue is, like calling, like the call to from, which is, you know, more convenient to get. But there is, like, when you get this error, like in the logs, you will actually see like other messages saying that, hey, it's called from here, this is called from here. I just haven't set up so that I see those messages in my in the editor here. But anyway, member function expected arg1 arg. But what you could do as well is you could just run, you know, sig build f reference trace, and you would get all those logs then. Yeah. Member function expected 1 arguments found 2. Right, so we don't need to provide that. There we go. All right. Okay. Let's go back to compile identifier, see if this makes sense here. All right. Now, the thing is here is that, well, this works. This probably works now for 1 depth. Like if the identifier is referred to an inner scope that doesn't have it, it goes to the outer scope to look for it. Or we're declaring the closure variable here, and then we return that. But then we also need to kind of hook it up later as well. So we actually need to kind of recursively declare these closure values. As well. So I think how can we do this? I think we just do like while lookup identifier name. It's kind of like we want to do a lookup, but we also want to specify which depth we want to look in. So let's say we have shallow true, and then depth is going to be like the starting depth, initial depth is going to be I. So let's make I here. And then I gets plus equals to 1. Okay. So while this is null, actually we'll start at 1 because we already did that. Okay, so we'll do a lookup. We'll look at, now we're looking at the parent scope, and we're saying that, okay, well, if we didn't find it there, we actually need to declare another closure variable for the parent as well. However, now we don't have the depth here, so we need like the initial depth. Let's just add a depth here that we just pass in there, and we'll declare u at depth 0, and this would be depth I. And yeah, I think that's it, because then whenever each loop I will be increased by 1, we'll do lookup again and see, okay, well, if it's null, we need to declare another closure variable. If it's not null, that means we found the scope where it exists in, and so then we're done. So then we can continue. So there we go. I think that will kind of handle any depth that you find an identifier in, and then hook up every parent. And if we get here again, then we already have defined it in the scope. So then we would find the lookup, it will be found here, and then just short circuit here. So that should work. So now we have the closures defined. Now we just need to wire it up so it actually adds these instructions when we compile this. So also another thing we need to do is we need to add the scopes whenever we should. So we have, for example, we have compile block here. This should have its own scope. Like, I think basically every time we have an instruction set, we actually need to have those needs to have their own scope. So here's like we're saying, okay, well, now we're targeting this set. So we basically want to push the scope now as also. Push. So this would be scopes and then push. Okay. And then whenever we change this back, we also pop, because then we're done with that set. Okay, so now the context of this block instruction set is going to be ran in its own scope. So any reference to identifiers will be brought into the closure now of this scope. Okay, now we need to do the same for executable call. Basically, anytime we're doing this part here, we're adding instruction set and we're doing this. Also, the fork is basically gonna happen every time as well. Push. So let's just wait. Why is that? Oh yeah, okay. There we go. And over here, we're gonna do scopes pop. All right. Function call is kind of weird right now. No, it's not actually. Well, we're forking, but we're not. Yeah, that it's where the function declaration is. The function declaration. Here we go. Here we need to do push. And then all right. Let's see where else we're doing this. I mean, yeah, we're doing it here, I guess. These don't really refer to any identifier, so that's fine. We've done that. This one, pipeline. Oh yeah. That is correct. So the pipelines, yes, this definitely needs that. So there we go. And then after, let's see here, it's waitable. I don't think we really need to have this in its own scope here. Don't think so. Well, let's just do this here to be safe. Yeah. And then the last set as well. Okay, this one is done. This one is done. Okay, and then we looped around. So we have our scopes defined now. And I think if we go back to the code here, so when can we say that, okay, well now we're kind of done with the closure definition, so we can go ahead and compile it? I think it's whenever we are at the end of the scope, right? So whenever we kind of pop the scope, we can go and look at the scope and see, okay, well, we got this closure we need to define. So let's go ahead and do that. And then we add those instructions in. All right, so and basically the instructions we need to add is basically whenever we fork into, it's like before the fork we need to do this. So it's like the fork instruction itself needs to add these instructions. I mean, maybe I was thinking like maybe we build it into the fork instruction to actually kind of do this, but the problem is that this is like a dynamic list of things. No. Okay. Also, we need to make sure we don't mess with the R register. Maybe we'll use the stack. So we're kind of before you create a closure, we store R, and then here we're using it, and then over here we should actually, because this could technically use R, so we also push here as well. So this would be like ref closure, and this would be like the saved R. And then, and this would be, then I have to like set saved R equals R, set closure equals R, and then this would be like, well, this would be closure, and this is whatever, and then here is the closure pointer, and then at the end we restore R. So we set R equals saved R. There we go. I just need to refill my coffee. I'll be right back. Okay, so let's see here. So this is kind of the procedure of like creating a closure here. So now I think it's like whenever we do self scopes pop, this is where, except for maybe here, this is where we need to create the closure if we have one. If we don't have one, we don't need to actually create it. So yeah, so before we pop, we want to, well, this is gonna be at different places. The kind of weird thing here is like when we do the fork instruction, we want to have access to the closure actually, but it might not actually be so yeah, so it might not actually be like needed, but I think we have to create a ref here. So this would be like closure ref, new ref, closure, okay, And of course we need to change the fork to also get the closure ref, which is a location. And I guess we'll add it here as well. All right. Whoops. Okay. And we will put that there. So it might be used, it might not be used, but now we have it. Hello, V Secunda. What's up? Welcome. Hi, are you making your own custom IR? Yes, you could say that. Although it's not going to be used for compiling, well, probably, I should say, not going to be used to compile to native code. But it is used for the interpreter that is that is running this in like a virtual machine. You could say like a, you know, not a virtual, like not an actual, you know, virtual machine, but kind of like a simulated, like an emulated machine, you could say. Well, I'm not emulating an entire. I'm kind of, well, okay. So what is emulated is basically virtual threads. So we have like virtual threads, and then like, you know, registers, you know, memory space. So heap, stack, and also read only as well. So that is kind of what is emulated. And right now I'm working on kind of like closures for the virtual threads, so they can refer to variables from outside. So this is run in like a separate virtual thread here, and X refers to like something way up here, which is like way outside of the scope. So that's what I'm working on right now. Basically, we're creating closures for each thing here to be able to refer to things outside. And the closures are on like the emulated kind of heap. And yeah, well, this ref, well, this ref is like on the stack, but it's gonna be actually, this is kind of weird because yeah, what's gonna happen is so how I made this here is that every time we call these functions, they will modify a list of instructions, right? And then the idea was that once you've done that, those are the list of instructions that we have. But what I need to do now is kind of like a conditional list of instructions here that might or might not exist, depending on things happening over down here when we actually compile like the inner parts of this, where this thread is going to execute, to know if it actually refers to to know if it actually refers to like identifiers from outside. But I mean, maybe we could do like static analysis instead to try to build the scopes up like that. But we could also do like maybe we'll create a special kind of instruction here that will kind of expand or something once we're done. Maybe. That's going to be like a more, it's going to be like an abstract instruction. We don't really have that right now. All instructions are basically like a source code. They're like serializable into a source code, and we don't really have abstract instructions that then later gets changed. But I guess that's what we need if we want to do that. And that could include this closure, perhaps. Yeah, because this is gonna be. I think we dereference that to get the pointer to the actual heap. Yeah. Because this is a pointer to the stack. It's just a place where we store the pointer to the heap, to the closure that's on the heap. So if we dereference here, this now turns into the pointer that points to the closure on the heap. Yeah. Okay, but do we want to have like abstract instruction? How do we do this actually? It's either that or we create like a marker here, like the index. So we create like closure instructions, so like create closure index, which is going to be like self instructions. So that's like the current index where we would insert a bunch of instructions later. We could do this. Yeah. And this is the only thing that actually does this. So it's probably, yeah, it's safe to do this. Because, yeah, we could potentially have other things that does the same thing. And then the index would change, you know, depending on if you insert things before. That should not happen after this. Like this index should be stable is what I'm trying to say. I think. Yeah, there's nothing before this that's gonna change in this compilation unit. No. So over here, now we can we can say that now we can have a generic function that will say, okay, well, compile closure initialization okay. Yeah, that should be all we need. Oh, yeah, we need the index as well. So the index of where it should be inserted into. And here we don't actually have a result. Okay, so what's this gonna do? It's gonna basically compile this part, except for the ref, because we already have the ref. Oh yeah, we need the ref as well. But it's gonna do this part. I'm gonna copy this, put it over here. So we have the index where the instruction should be, and then we have the closure ref as well. All right. So first we set oh shit. The thing is here that we are using, like if I was to use, like we have these convenient functions like set, you know, this would actually create the set instruction. However, it just adds it. It just adds, like appends. Or wait, add. Yeah, it just appends it here. Maybe we could have like insert as well, but then we would need to change so many things for that to work. Also, we probably want to have like insert a list to be more efficient, probably. I don't know. Insert slice. Is that a thing here? Do we have insert slice? Yes, we do actually. Okay. Cool. So allocator index. Items. And that would insert items at I by moving that to make room. Okay, cool. Right. So we'll create this thing. I mean, what we could do is we could make a set, although the set would kind of be, because no. Actually, one thing that is not really stored in the context is like these refs are, they have to be kind of comp time known. It's kind of like, I'm drawing a parallel to React. I'm not sure how many are familiar with this, but basically in React, whenever you have like a hook, you cannot have like a conditional hook, or you cannot have a hook that is called conditionally. You have to call every hook the same way every render. It's kind of the same thing here, because otherwise the address of this is not comp time known. So I have to create this ref over here as well. So we have the closure ref, and then we also have like the saved or ref. So I'm gonna say like closure to do that, save or, because technically or could possibly be used when we fork, and that's why I'm doing it like this. Okay, so we have these two refs are now there. Good. And then you would need the index, which is like closure, create closure index, and then the closure ref, and then we also need saved R ref. Okay. Now we will create instructions, which would be a list of instructions. Let's actually make this into like an array list. Right? And then we can use it to as a slice later. So first we need to set saved R to R. So we just append. Actually, we could do append assume capacity. And then we'll initialize this to capacity. And the number of things is going to be 1, 2, 3, 4. And then plus how many closure values we have. And then plus, and then 5, 6. No, actually, fork is not part of this. Oh shit. This needs to be afterwards. Okay, so I guess it's 4 plus these. Yeah. You know what? We could pass the index to the fork and then we don't, yeah. Because it needs to kind of surround the fork with this. So the instructions, that this is going to be the pre-instructions then. Which is going to be, you know, 4 plus closure. So 4 plus, and then we need the frame. All right. So this will be closure items length. Okay, and then you are actually source. I need to do like from, and then type. So I think it's like this. Set, maybe, no, or is it this? Okay, I didn't have that convenient function, so let's just do that. What's the issue now? This is weird, like the yeah, as long as there's like a weird syntax error. Okay, destination source, right. It refuses to kind of, you know, the auto completion refuses to work. So destination, yeah, and then wait, what was the other one? Source. Okay, so destination is the, no, it's this ref here, yeah. So that's a location. So I think it's just closure ref. Or does it have to be dereference? I don't remember actually. Let's check this evaluator. So if we have a ref, the destination is always going to be dereferenced, it's not gonna point. It's not gonna be like the stack pointer. And if we dereference again, that's gonna dereference again. Okay. I'm thinking of changing that to actually this means like setting, like, because this acts like a kind of like a magical pointer right now. We're not actually setting like a dereference here. This actually means this. It's not setting like the pointer itself. So there we go. So the source then is gonna be this. So that's gonna be like init. So do we have from location? Yeah. So this is gonna be register R. Alright, so that's that instruction. Now we have allocate to. So we have alloc. And I think this is a simple number. Yeah. Okay. And then we have ref closure, although we don't have ref closure. Oh. So actually we only have 1, 2, 3 instructions plus length. And of course, yeah, you need to be tried. So now you're correct. Alright. Alright, so we got this one, we got alloc 2. Actually, it's it's not 2, it's gonna be like the closure length. So I'm gonna call this CN for like closure number, or CL, closure length, maybe. Okay. Set. Okay, so we can copy you. And here we set. Now. Oh, okay, this was wrong. This is saved R. Here we set the closure ref to be R as well. So kind of the same thing there. And now we set all of these. So now we actually need to loop through all the CLs. And we can copy the set instruction. And we can say destination is going to be closure ref. And we actually need to kind of deref this. Yeah. Okay, actually, you know what? This is kind of stupid that this is closure ref. Because at this point, R actually points to the correct thing anyway. So we could just use R, because it's a hassle to use the closure ref now. So actually, this would be init add. And then abs is register R. This is I, and then this is dereference true. So R is pointing to the closure heap in the heap, and then we add whatever address points to where these should be. Okay, and we dereference to set that location to the thing we need to set. And what do we actually need? What do we set here? So X, so this is going to be a simple, I think this is just going to be a lookup. And it's guaranteed to exist. So this is going to be like, I'm pretty sure we can do a simple lookup and the name is frame closures. Wait. What's happening? Oh, it's this probably. Closure items I dot name. That's the name, and then we look that up in. Hang on. Okay, now I need to think about which scope are we in. I think we're in the parent scope right now. And that is correct, yes. So, and then you are shallow, I mean, that should be true, although it shouldn't make any difference, but it should be true, and then this has to exist, so I'm just gonna unwrap that here. If it doesn't, that's like a compiler bug, so I'm just gonna force it there. Should be fine. Should be fine. All right. So now we should have all of these instructions there. Now the question is though, if this is, because we kind of declared these straight up before as not being dereferences, so they are basically pointer. I mean, I think that's fine. Yeah, that's fine. All right. So now, actually, no, this can't error. Yeah, so we don't need a bunch of tries in there. And you can't error. You can be a, yeah, but that doesn't matter. Okay. Now, can you be an error? No. Okay. So, right, the fork is already done, so we don't need to do anything with the fork. Do we actually set the closure somewhere? Yes, we do here. Okay. And then we have, and then at the end, after the fork now, we need to actually set R. So that's going to happen after the fork. So we need like post instructions. I'm just going to do the same. Even though it's just one instruction, I'm just going to do the same for no reason here. The same, man, what was the word that I was, ritual, that was the word that I was looking for. And we just need one here. And I'm gonna copy one of these set instructions, and this is going to be post instructions. And we assume capacity, you are gonna be, destination is now the R register, and that is going to be set to saved R. And again, I have to check if I need to deref this, because this is technically a pointer. I think I need to deref this to actually get to the content of the ref. So I'll just look into the evaluator, and I will look into the source. And no, I think we actually need to deref that. Yes, okay. So there we go. Otherwise we would set R to like the stack pointer where this is stored. Now we're getting the actual value stored in there. Okay. So I think now we have the post instructions, we have the pre-instructions. The pre-instructions should happen before the fork, and the post should happen after the fork, of course. So I think what we'll do is we'll probably add post first, because that won't mess with the index. If we add pre, that will mess with the index. So just to play it safe, I'm gonna do let's see where, so current set, and then insert slice, and then this would be the index, and then the instructions are gonna be post instructions. And to turn this into a slice, you can do toOwned slice, which will also free up the thing, or it will kind of oops, it will empty the array list, but the memory is like owned now by the returned place. Okay, so that is that, and then we need to insert another slice, except this would be pre the fork, so this would be before. Okay, and this would be pre instructions. Also, I think this needs to be, yeah, we need to try those things, and this one as well, I think. Okay, so now we're kind of modifying the instructions after the fact, after we've done a bunch of stuff, and we've figured out what closure variables we're referring to. Let's see, let's hope that this works. Okay, we also need to fix the fork instruction now, because it needs to be able to, it needs to push the closure as well. So if we go to evaluator, we have the fork instruction. So here we're pushing 3 things on the stack, but we need to push another thing again as well, I mean. So we need to push the closure as well. All right. Which should... Okay, this needs to be dereferenced. I just realized, I think. So when we do, when we set closure ref, it's gonna be set to R. But the thing is, we know it's a ref, so actually over at the fork instruction, yeah, we are dereferencing. Okay, good. Cool. And now I think that we just need to add this same thing to basically all places that creates forks. Oops. Wait, I also forgot to modify the index. So this index here should be, I think it should be after the fork inherit. Because technically, like, let's say you're inserting at index 0, that means it should be inserted before the current item that is residing at index 0, right? That makes sense, because you're not saying like -0 or -1, I mean. That doesn't make sense. So it's like so the index that we need to provide would be the fork. I mean, technically it could be at 0, so probably we want to not take -1 here. Probably we want to do like +1 here instead. Because if the fork is at 0, now this would come after the fork, and this would be before. Yeah. And the index that we send in, where are we? Here. Needs to be, so if we're at, yeah, this is correct, I think. It's gonna be the index before, yeah. Because if this is the first instruction, let's say, this would be 0. So that's fine. All right. Okay, now we need to do the same thing at the other places as well. I think basically these 3 things could be maybe like, what you could do is you could create closure context, and then we would have like closure ref and save R, and also the index. Okay, and then we'll do like closure equals create closure, or compile create closure basically. Yeah, and we don't actually need anything. And then this would be like closure context. And then we take these things and we put them over here. And we return closure ref. Save R. And index. And I would prefer to have them like this because and not like call this directly here, because I just want to make sure the order is correct, like the order of operations here. Actually, it doesn't really matter. No, it does matter. This needs to happen last. Yeah. Yeah. Okay, so now we have that context. So now we can just call one thing to get the whole thing. Now we can say closure dot there. And over here, I mean, yeah, here we can just pass the whole closure actually, instead of all of these things. And yeah, now we can do this. All right. Oh, and the index. Yeah. Okay. So now it's a little bit easier to call this now. So you just call this to create a closure. You use it here to pass into fork, and then before we pop, we compile the initialization as well. All right. So we don't have to copy too much things basically. Okay, so whenever we do this, we want to do this now. So here, where's the fork is happening over here? No, that's another. That's not the. That's fork. I think the forks are happening up here. Yeah. The last set. This is the first fork. And here's the other ones. And then the last fork. So there's like 3 different things here. So this would be like first closure. This, oh, we need like, yeah, we need 1 for each of these. Okay, well, I guess we need to make a list here. Stage closures. Yeah. Okay, and then right. So we will do like stage closures. I mean, we need like a high as well. Equals. No, wait, this should be like +1. Wait. Stage sets. Hang on. This includes the first one. Okay, my brain just went into like it, I felt the energy just sap away right now. I had a flow there, and it got like it got interrupted somehow. It was like, yeah, because I think it's because when I added stuff, I didn't face any issues or larger issues. Now it's like, okay, well, now this doesn't really fit into the pattern, so. But yeah, okay, so let's actually make. Also, how would we compile this later? It would have to be when we push the scopes and then pop it. Like before we pop, we compile the closure for that thing. Yes. And does that include the first stage? I think so. I think all the stages are, for this part, I think they are like generic. Except for the last set, I guess, here. Yeah. The last set is different, but then these are all the same. No, wait, yes. I guess they are. So the last set is different because then we wait after. But that we wait as well. But the pipe, okay, the pipe is not set to close or to keep open, I think. Okay, well, anyway, that's not the problem we're trying to fix. So basically, all right, let's just do stage closures 0 here. Let's keep the same pattern here. Stage closure 0 is equal to that. Also, we need to add source. And this one is also compile, create closure. All right. And then the last one as well. Except this needs to be separate. So this is like the last closure. Okay. And then over here, before we pop here, we're gonna do compile closure initialization. And the closure that we're referring to should be like, well, we could get it from here. We just add it there and get it. Stage closure. Doesn't need to be a pointer. There we go. And the same thing here. Yeah, crucially, okay, yeah. Excuse me. The instruction set also, it actually needs to be set back to the original before we compile. Otherwise, it will end up in the wrong instruction set. So I have to do that as well. Before I didn't have to do that because we constantly changed it over here. But now, since we need to compile the thing before we pop, we actually need to set this here as well. All right, now and then this one here should be good, except this is the last closure now. All right, okay, cool. Now, where else do we have this thing happening? Compile initial. Actually, I want to go back to compile pipeline. Because there should be forks in here that has errors, yeah. So this one we set... this one should be like stage closure 0. Closure ref dereference. And here, same thing. And over here, same thing, except this last closure. All right. Oh, right. We have these ones that doesn't really matter. I can't really put undefined though. But the closure is never gonna get referenced. I'm just thinking of what kind of null value we could use for that. That's not gonna crash and burn the thing. Do we really want to introduce like a null pointer thing? What would that be? Init. So what it means is basically something that is not supposed to be used. So actually, like, it shouldn't matter what it is. It's just gonna be something that you could use to say that this doesn't matter. So I'm just gonna say I'm just gonna say the OR register. That's very simple. Oh. All right, let's do that. So now you can just say this to say that, well, this pointer doesn't matter. There we go. Same thing here, I believe. Yeah. Should it be null or nil? Nil is from Lua. I just realized, like, nil, like this. Or is it? Or was that Python? Or I don't remember. Anyway, null. I mean, actually, you know what? Let's do like, this is the Swedish word that means 0. So let's do that, actually. And it kind of has the same pronunciation. Null. Noll is the correct pronunciation there. Okay. Let's see. Do you care? What do you want? No, you don't have any. You don't care about that. So there we go. These doesn't have any closures. There we go. No field name initial depth. Right. Oh yeah. Okay. We need to implement that. Initial depth. Start at 0. And this would be options initial depth. Right, these ones we don't care about. We can remove those. You need source. So just a little bit of cleanup now, then we can test if this actually works. There can be an error. There we go. You are a constant, so these need to be variables or mutables. Expected 3 or right. So you function call, right? Function call. Interesting. I mean, yeah, this would also require a closure. The issue here, though, is that the declaration that we don't really have the scope here. Okay, this is a conundrum. It's like we declare the function, the scope is where we declare the function, not where we call it, but where we call it is where we need the closure to be created. I mean, I guess we could store the closure context in the declaration somehow, like in the reference. Yeah. So we have the address. We also need the closure context. So we actually need to kind of move this. Out here. Although, okay, actually, no. The index, no, okay, no. The index doesn't make sense. What do we need to, what do we actually need? No, we need, what do we need? I think we need these. And then the closure, and then the scope as well. Okay, you know what? This is a little bit more. I need to think about this. I'm gonna add a to-do here. How to implement closures here. All right. And of course you need a closure, but I'm just gonna say this for now. Mobile function is 6 arguments found 5. Oh yeah, so well you okay. Hang on. Oh yeah, so we haven't done it here. The fork thing. Actually, why are you happening at the bottom? There was like an issue with this that we had before, where the fork needed to be happening before we do all this thing. For some reason, I don't remember what it was now. Why would it need to be happening over here though? We have the set. Let's move this for safety purposes. It doesn't matter, like the order doesn't matter because this is happening in a separate set. So we do it here, and we also do now the closure. And of course it's going to be closure ref, the reference. And then before the pop we will do compile closure initialization closure. All right. Okay. Now we're over here. Structure. Oh yeah. So we look up. We get a result, and the result always has a source, so that's what we need to grab out there. There we go. Expected, oh, out of memory. Wait, why did why did I add that there? There we go. Okay, we're out of compiler errors. Well, for the Zig compiler, we might have errors when actually running this code. So, okay, we're fresh off the compiler errors being solved. Now comes the question, will any of this work? No. I'm just gonna, okay, so we don't have any instructions down here. I'm just gonna do like another very simple example over here. So I'm just gonna say like bindings. So I'm gonna do like basic or bindings basic. And so I'm just gonna say like hello world echo s. So even this simple, very simple example, s is evaluated or compiled inside another scope, because this expression here is ran in a separate thread. So s is actually now referring to the outside s here, which points to the read-only data of this. So let's remove this. Let's see if this, if I can compile this. Oh shit. Okay, I think we ended up in some kind of infinite loop, maybe. I'm not sure. It took a while to do this. Yeah. 40,000 lines of execution here. Okay, so let's see what this compiled to. So here's the results of the compilation. We have some read-only data, which is this part here. And here's the instructions. So these are like always in every program. So this kind of sets up the streaming of the standard I/O pipe. So standard out, standard error, and standard in. Okay, and then we have ref. Yeah, so here's the closure that we see here. So we have like the R saved R, we have the closure ref. Here we set R to be, or we're saving or storing R in here. Here we're creating closure. We're setting now. Okay, the thing is like, okay, you know, technically this doesn't need to be in a closure, of course. And why? Because this is like a read-only. So this is like a comp time known. So you know, potentially this could be like a compiler optimization. But right now it's like, okay, well, we're just trying to figure out if this was like a dynamic. Let's just imagine this was. We're just trying to make this work here. So we're storing the closure, we're creating closure here, allocating on the heap, and then we're saving that to, we're saving the allocation pointer, which is now stored in R, to the closure on the stack here, reference here. And then we're setting the closure content, the first one, to be stack 3 plus 0. So that's that's a pointer, right? Okay, and that should be good. Stack 3 plus 0, that's a pointer, yes. Okay, I think this is a pointer, but it's like we need to but the problem is we need to kind of dereference S3 to get the... Okay. Let's just see what's happening here. So then we push this on the stack, which is should be pointing to the heap where this is. Now we could run through this. We could run this through the debugger to actually double check everything here, but I'm just gonna look through here first. Okay, and then we restore our. All right. Oh yeah, we forgot to push or pop. I mean, we actually forgot to pop this. I'm just gonna do it right now while I have it in my mind. So whenever we do those create closure things, we create 2 things on the stack. So we have to pop 2 things on the stack later. So when we do the compile closure initialization and we pop, actually we need a 3rd thing here. No, we don't, because we're setting the instructions to later. Yeah. Okay, but where do we actually pop this though is the question. I think we just pop it after here. Yeah, it should be safe to pop at this point over here. So here we just pop those 2 things off. So let's just do it at post. See? Keeping this ritual was good, because now we can have the ability to actually add more things over here. Let's just add this. We'll add this here as well. Pop. 2 pops. And that's just a void, so we can just add 2 pops there. And we need to increase the number of instructions. No, that's post instructions by 2. There we go. All right. However, I don't think that was probably not the big issue here. All right, and then we wait for R. Oh. Okay, this is an issue here, because we expect R to actually change after the fork. So actually, I don't think we even need to restore R. Where we need to restore R is actually over here. Yeah, okay, that was stupid. R actually needs to be restored over here. So that whatever fork is referencing, R is like intact. But then after fork is, after this, so fork always sets R to the thread handle that is created when you fork. So we actually need, also pop does change for, pop actually changes R as well. So actually we need to push R here and pop it, actually. Oh shit, we can't do that though. We can't push and save it. Well, we did save it in saved R, so I guess... No, we need to save the R from fork. Okay. I mean, I guess we can reuse that. No, we can't, because we're popping it. I mean, if this was actual assembly, it doesn't actually matter, pop, because the stack, you can refer to, I'm pretty sure, you can refer to things after the stack counter. However, the way that I've done this, so if you try to refer to things after the stack counter, it's actually going to crash the program. But it has to be a simple way to solve this. I mean, we could wait with a pop, I guess, at the end. We just have to make sure that R is actually changed after this. No, that doesn't make sense. This has to be solvable. We store R here, right? What we want to have is fork the R needs to be saved after fork. Okay, what if we do this instead? I mean, we're popping these, so we don't really care about the contents, right? So what we can do is we can say that, okay, well, depending on which one is actually used, depending on which one is which, is the saved R first or the closed R, or the closure first? So saved R is first, so that's the last thing to actually be popped. So what we could do is we could say, okay, well, before we, after here we want to set, we want to set saved R to be R. So we store the thread handle from fork in saved R, which is this pop over here. So now when we pop and pop, we actually restore the R from fork. I mean, we could also do this just to make sure, but let's just do that. All right. And we can just copy this one because this does the same thing. But we need to add the post instructions there. All right, so now we have 3 things in the post. There we go. Cool. Oh yeah, you need to be pre. Okay, yeah, we're restoring R before we call fork, and then we call fork, R has been changed, we store it again in saved R, we pop closure ref, and we pop saved R, and now R should be restored to the thread handle that fork returned, and there we go. Cool. Now, and then the rest of the instructions should be working as they should before. Okay. And I think I want to increase this by 1 because we have 1, 2, 3 plus length 4. Yeah. There we go. Okay. So now we're actually now it's popped. Okay, now it just exits immediately, or well, not immediately I guess, but we don't get any output. So this is kind of what you would expect actually from this instruction here. We're streaming a little bit and then we exit, but we don't get any output to stand it out for some reason. So let's check the instructions again here now. So we have this these refs here. We set you to R. We allocate one thing, and we set that to R. Yeah, because that's the thing we set. Yeah. Yes, and then we set you to stack 3 plus 0. That should be correct. Or is it correct? Actually, this is a pointer, so I guess it is correct. There's something here missing, I think. And then we set R to be this closure saved R, yeah. And we fork, and yeah, we restore R, we fork it, we set this to R, we pop, and we wait for that, and then exit. So that seems good. And then down here, we are, what I'm thinking is missing is basically when we populate the closure, we should populate it, you know, with the actual value, the actual pointer, which we're not really doing here, right? We're actually setting it to something. This is not correct. Okay, and then in this one we create a string with 3. Yeah, this is this string we're creating here. And we're setting the length to 2. We are setting that the ref equals R. That is right. That is the pointer to the heap. And then we set R to be the dereference there, and now we can use R to kind of populate the thing. And now this is the kind of thing that I would expect to see here. This is the read-only data. Well, it's actually like an empty string because it's at +0. That means 0 length. But this, no, yeah, and then you see this one. This is like stack 3 plus 0. So it's like that refers to now the closure, although it's a pointer to the closure. Okay, I think what we need is we need 2 different versions of the thing. We need one when we declare the closure. Okay. So this declaration is happening in the inner scope. And that should be the stack 3 there, but it should, I think it should be dereferenced actually. Yeah. All right. But then the location that we return is actually not gonna be the same location, I don't think. Or do we even care about this location? I think we don't. The location that we return should be like the lookup value of what we are trying to get. I'm pretty sure. Or it should be like it should be the previous closure or the previous scope's value, I think. This is a little bit of a brain twist here. So we compile the identifier. That the inner thing should refer to the stack dereferenced. Yes. Well, the stack pointer dereferenced, and then what we have, and then what? Okay, I lost the thread here. Yeah, okay, so the inner so the identifier in the inner scope refers to the stack, the reference pointer, yes, where the closure is, and then then what we populate the closure with is different. So actually, okay, that happens somewhere else. Yeah, so this should be correct. This should be the same thing, yeah. That should be correct. Actually, I think we dereference the whole location. I'm pretty sure. Dereference. No, that doesn't work. I'm not sure if this works here, or if you have to add location. Yeah. Although this doesn't work either because it's not mutable. Alright, there we go. Yeah. And then what else do we have? We have compile, create closure. No, closure initialization, I think. So this one, when we set these things, man, why are we getting like the stack for this? So the scope that we are in is actually the inner scope right now. I think we're in the inner, yeah, because we pop after, so we're in the inner scope. So we're trying to populate the inner scope closure, which means we need to grab these from the outer scope, which means we need to set the initial depth to 1 here. Okay. I think that's better. Still no output. But let's see what we store here now in the closure. There we go. Now we're storing the actual like read-only data here. Okay. But still no output, so I'm not sure what's going on there. What about over here? This also refers to this. Okay, this is this wrong or correct? No, I think this might be correct. Maybe. Huh. But what is this though? Okay, I need to go through what's going on here. So we're creating a string. That the string has 3 values. The first is the length of the string, and the other 2 are like the 2 elements. And of course you can see it should only be 1 element, but there is like a slight quirk in the compiler right now where if you have an interpolation you also have like an empty string before. So I just haven't done with that. But that's why we have 2 elements. So we have 1 empty string and then we have the interpolation expression. Okay. And we're storing the pointer to the string here. And then we're setting R to dereferencing that. So we can use R for storing the elements. So here we're storing element number 1. And we have +1 because the +0 is the length of the thing. Actually, we don't need to do set here though. We already it's already pointing to the thing. Okay, well, whatever. Oh yeah, I think we do it for every item in the element. So because they could potentially be like compilations in here that changes R. So, but anyway, then we set it to this read-only thing. +0, right? Okay. Yes, +0 is correct because that's an empty, so it doesn't really matter what this is here. 11. Okay, and then we say the second element is S3 +0, so that seems correct. Because S3 should be the pointer to the, should contain the pointer to the heap. And so this would be like, isn't this gonna be just a pointer to the heap though? So it's gonna be a pointer to the actual value we want to have. Maybe. And then we pop something and we push R. Right, so here we're preparing to call executable. And yeah, this is the echo thing. This is the result of the string. Compilation. Okay. Okay, let's do this. Let's go through with a debugger here. So we'll step through these. We have the closure here. So here you can see now we have these things on the stack. The first one is the closure ref. No wait, that's the saved R, and then that. So we're setting saved R to whatever the R was before. We're allocating the heap, or I mean the closure. R is now set to this address, which is pointer to the closure, and then we're setting the closure ref on the stack to that. Okay, and then we're populating the closure with the read-only data. So now we can actually look at that heap. Wait, did I implement that or not? Did I have a heap command? Yeah, there is a heap command. Heap address length. Okay, I just haven't implemented, I guess, the... there we go. So you need the address, which is... Wait, the address? Okay. How is the address parsed? It is parsed with like 16. So actually, if I put 11, we don't put like OX11, just 11. That's a hex. And then length is how many values I want to show. Right now, I think we only have one, but let's say 2, because we should see like some value and then null. Yeah. So here's like a pointer to the read-only memory. So this looks okay. This looks good. This is now the closure here. Like at this address, we have the closure. Okay. And next step is to restore R. So that should be set to thread 3. There, yes. And now we do the fork. So now the new fork should have, yeah, this is the pointer to the on the heap to the closure. So that looks good. Okay, now we're creating this string. Okay, the main thread is now storing the fork thread handle that we created. This is creating a thing on the heap. Okay, so thread 4 is the result of this fork, which should be restored at the end of this pop here. So we'll just make sure that that is happening. And now the inner thread is setting R to be 2. That should be fine. Right, after this R should be thread 4, I think, yeah. And we're setting the stack local variable to be the pointer to the string. Okay, now this is thread 4, so that is perfect. And then we're waiting for the inner thread. Okay, the inner thread is now setting the string. No, it's setting R to be the string pointer dereferenced. So now that's located at 12, makes sense. And we're setting +1 to be. Okay, let's actually look at that again. So heap 11. Let's just look at 4 values here. Oh, interesting, it said null, now it says void. I think void is the normal thing. I wonder why we say so null there. Maybe because we actually created like a reference before. I'm not sure. Or no, we didn't. Okay, I don't know. Anyway, we see this, and then we see 2 here. So this is the start of the string. This is the closure. Makes sense so far. And we're setting that again there. Let's look at this again. Now we're seeing this string has, or it's kind of like a slice of values or a slice of pointers, basically. It's kind of like a, yeah, I don't know. It's actually like a slice of pointers to strings, or things that can be turned into strings. So it has the length of 2. The first item is now an empty string. Okay. Second item is set now. Okay. Second item is set to a pointer to the heap at 12. Okay. That is not correct. Wait, why does it say 12? It should be like 11 if it's gonna be anything. So it's set to the stack 3, which is, oh, it's 12. Why is it 12? That is weird. When did it become 12? Wasn't it 11 before? Huh. Okay, hang on. I want to do this again. Let's see if we get back to that place. See here. Yeah, 3. Now it's 11. Set R equals 2. That should not mess with anything there. Still 11. Now we're setting you to be R. You're waiting. Okay, now it's 12. So this made it 12. Okay. Oops. Let's get back there. After this is going to be set to 12. That is wrong. Like this should never change. This like you're not supposed to change the closure pointer. So, or the compiler is not supposed to do that. So, what do we want to look at? So basically, this thing, we're setting this. Oh, this says this is the wrong pointer. This should say +4. This is the wrong thing. Why does it say +3 here? It should be +4. Compiler. So where are we? We are in compile. Something. It's not pipeline. It's like a call. And it's an executable. Yeah. Right. So this should be like 4. Didn't I change this before? Like, why does this work? This doesn't have a closure, so it doesn't really matter. No, it actually needs to be 3 because we don't actually have a closure here. I was certain I actually changed that to 4. Maybe I didn't. I was so sure. That is weird. Okay. Well, it needs to be 4 anyway. Well, there's the fork. Right, now it says +4, so that is correct. Okay, now you can see here, now the stack, the closure pointer is 11, that's correct. And then this is the string on the stack is correct now. Okay. So we're setting R to that, +1 is that. And +2 is that. So now let's go and check what the heap is. Let's add another value so we can see everything. Why does it say null there? I'm actually annoyed a little bit. Let's do 10. No, 11. 6. Whoops. Yeah, I'm not sure why it says null. It said like void before, but okay, whatever. So here's the closure. Yes, that's correct. Here's the string. It has these 3 things. Empty string. Now, this is a pointer up to the closure. The thing is, I'm not sure if this is going to be enough to be able to do this. Like, you have to kind of dereference this twice to make this work. I'm not sure if this will work, but I guess we'll, or if it should work. Execute. No, there's like an issue here. Yo, Code Guy, what's up? Welcome back. Alright, so there's some kind of issue here. integer-wise slice is active, right? Yeah. Because it's like it's assuming that we're gonna get like one type of value, but we're getting another pointer here. So I think we need to kind of dereference this as well somehow. It's like when you compile. Yeah, it's like the scope. It's like the closure declare thing. So this is dereferenced. It's just that the dereference also now needs to be dereferenced, because this is going into. This is the stack, and then we're dereferencing into the heap. But then the heap itself also needs to be dereferenced. And we're not supposed to add to the stack address, we're supposed to add to the heap address. So this is all topsy-turvy over here. Yeah, I think this is kind of the last thing we need to solve in order to make this work here. But I'm out of time now, unfortunately, so I have to leave now, but I will write this down. Yeah, I'm not sure how to do it. If we're gonna like add another type of location in the instructions so that we can kind of do like a double dereference at once. I don't know, man. Because that's kind of what we need at this point. Issue here when referencing binding it refers to the heap location of the closure, but we can't then index into it or dereference it without extension to the location mechanism. All right. Yeah. Yeah. Yo, Vincent. It is a little bit convoluted. It's just that the way we're declaring the variables here is like, yeah, it's a pointer, but it's like it's two layers of pointering. It's a two-layered pointer. Yeah, but that's gonna be it for this time. I'll try to think of maybe something else. Maybe we can solve it in another way. Maybe we can have a special location for. I mean, that's also a little bit convoluted, but we could have a special location for the closure, which would automatically be like the correct place, like the stack 3. It's already dereferenced. So if you dereference that, that's gonna go into the correct thing. But yeah, that's it for this time. So thank you very much for joining me, and hope you have a nice day, and I'll see you later.